Uh, Hi, I am Aarti, and today I will be sharing a demo in which I'm going to show you my ROS Odometry subscriber program running with TurtleBot3 uh, uh, in Gazebo. So the goal of this assignment was to subscribe to the /Odom topic, which is published by Gazebo, extract the robot's X position, Y position, and yaw orientation, which is its direction, and continuously display that information to the screen while the robot moves. So I have the 4 terminals open, and let me walk you through one by one what each of one of these terminal is doing. So in my terminal 1, uh, I have launched Gazebo with the TurtleBot3 world, and the command that I run was export TurtleBot3 underscore model equals to burger. The second command that I'm going to run is ROS launch TurtleBot3 underscore Gazebo TurtleBot3 underscore world dot launch dot py. So if I press enter, this will start the Gazebo simulation and spawns the TurtleBot3 Burger robot into the world. And the Gazebo is the program that physically stimulates the robot and publishes the /Odom topic with the robot's real-time position data. So you can see the Gazebo has been already launched simulation, and the robot is placed over here. So I'll just zoom in so as to show you how the robots look like here. So you see this is our robot, and it's going to move around our simulation. Now let's have a look at our terminal 2. This is my pose subscriber node, and the command that I am running is ROS to run my pose underscore cpp my pose, and this is the program that I actually wrote for the assignment. So it subscribes to the /Odom topic and prints the robot's X, Y, and your direction to the screen every time a new message arrives from Gazebo. So now let's have a look at my terminal 3. This is my teleop keyboard controller, and the command that I ran was ROS to run TurtleBot3 underscore teleop keyboard. And as I press enter, this lets me drive the robot using the WASD keys from my keyboard, and W will make my robot move forward, X will make it move backward, A turns towards the left, D turns towards the right, and spacebar stops. I usually use S instead, but you can use either of these. So as you can see, I'm pressing W, and the robot starts moving in the simulation. The more I press the same key, it would increase its velocity. So the many times I press W, the many times I press X or A or D, the angular velocity or the velocity it would increase. And simultaneously you see it reflected in the terminal 2 as well. But now let's have a look at my terminal 4. So in this, okay, so you can see my RQT graph has been generated over here. I've run the command, and okay, I can hide this now. Okay. So in this gives us a visual diagram of all the nodes and the topics which are connected in the system. And let me explain what is being going on over here. So on the one side, you can see the teleop keyboard node is publishing velocity commands to the command well topic /command well topic. Gazebo receives those commands and moves the robot in the simulation. Gazebo then publish the robot's updated position on the /Odom topic, and my node, which is the /Odom subscriber, which is my post program, and is subscribed to the /Odom, which reads that position data continuously in real time. So this is the full pipeline from keyboard input to the position output on the screen. You see here it is my Odom subscriber. Now let us look at my terminal 2 where my pose node is actually running. Okay, so you can see over here, it's printing 3 values on every line. The first is the x coordinate, the robot's position along the x-axis in meters, the y coordinate, which is robot's position along the y-axis in meters, and the yaw, which is also called the theta. It is the direction of the in which the robot is facing, also measured in radians. So right now, the robot is not moving, so the values are staying the same. So if I start driving it around, you will see the values will be updated live. I'll be clicking on this terminal 3 in the teleop keyboard to make this video active, and then, okay. So I'm pressing W several times over here, and you can see in the simulation, the robot is moving. X and Y position values are also changing as the robot moves through the world. You can see in the terminal 2. The yaw value is initially staying the same, but when the robot takes turn, it changes. You can see yaw is actually measured in radians, and when the yaw is 0, the robot is facing along the positive x-axis. Positive yaw means the robot is turning left, and negative yaw means it is turning right. Okay, so you can see I've been driving my robot a lot over here. So you can see all these 3 values are changing together. Now it is being stopped now. Okay. So now let me walk you through my code that I wrote for this assignment. So over here in the terminal 4, I would be opening my post.cpp. So here you can see I'm running the cat command, and ROSbot classwork is my worksheet, the folder in which I have done this project. And then there is a source src, my pose cpp src, and then my pose.cpp. Okay, I'll just increase the window size over here. All right. So my program defines a class called Odom subscriber that inherits from the RCL CPP node. This is the standard ROS2 way of writing a node in C++. So in the constructor, I have created a subscriber object, which uses like create underscore subscription. You can see it over here. This is the constructor over here. And the node Odom subscriber, it is mentioned. And this subscriber object is, it gives us like 3 things. First is the topic name, which is slash Odom. And you can see it over here. This is the slash Odom over here. And there is a queue size, which is of 1000 next to it. So that's the second thing. And the third thing is a pointer, which is like pointing to my callback function, Odom callback. The callback function is the most important part. ROS2 automatically calls this function every single time a new odometry message arrives from Gazebo. And now let's have a look at my callback. Inside the callback, I extract the X and Y position directly from the message using the message. And you see here it is my callback, and then the message pose both for like X and Y I have defined over here. It's of double type. And for the yaw direction, the robot's orientation is published as a quaternion. That is the 4-number mathematical way of representing 3D rotation. You can see it over here, X, Y, Z, and W over here. And I've used the TF2 library to convert that quaternion into roll, pitch, and yaw. For a ground robot like a TurtleBot3, we only care about yaw, which is the rotation around the vertical Z axis, basically which the robot is facing the floor. And finally, I use the RCL CPP underscore info here. Okay. So what it is doing is that it is printing all the 3 values to the terminal on every message. And down below, I have down in the main, I have called the RCL CPP spin, which keeps the node alive and continuously processes the incoming messages until the node is shut down. Without RCL CPP spin, the node would start and immediately exit without ever receiving a single message. So this is the code that I've written, and thank you for watching.